Okay, so let me see, make sure everything's okay. Okay, so basically today what we're going to do is to kind of finish up the chapter one. So just to give you a heads up, I remember on Thursday I mentioned that there's a lemma that I want to come back with proof. But after I thought about it over these 2 days, I realized that I don't think that we really have time to go deep into that. So if time permit today, I will probably go back to the proof. If not, then what I'm going to do is just to write down like the schedule proof, because the proof is actually in the textbook, but this a little bit subtlety. I don't think that the textbook is 100% correct, in the sense that they're not very careful about a particular notation. So if I don't have time to come back to that proof, then I'm just going to write down on my notes to point it out what's the key part, and pretty much it's similar to what the textbook was doing, but just to fix the notation a little bit. And then I will post the notes so you can actually read the notes by yourself. Okay, so one goal for today is to actually continue the manifold with boundary. Then we will move on to the smooth map and smooth function. So let me quickly recall that what's the manifold with boundary. So last time I drew this picture where, I mean, this is just some indication picture of manifold with boundary, right? So you might have a surface like this, but then you can see that there's an open up here. So I want to be a little bit like sloppy just to tell you. So manifold with boundary, topological manifold with boundary is not necessarily a topological manifold, as I mentioned last time, because it's not locally Euclidean anymore, but it's actually locally homomorphic to the upper half space. So the upper half space is basically, I'm going to use this indication like just as in R2, but think of it as a Hn, right? Where everything, the nth coordinate is bigger than or equal to 0, right? So it's sometimes I would refer to it as upper half space, right? So basically this axis is when xn is 0, is usually what we refer to the boundary of the Hn, right? And the whole thing is just the Hn. Okay, so, and this is the interior of Hn, right? Everything inside here is the interior. So everything is the same in the sense that to qualify as a topological manifold with boundary, you still need the Hausdorff, okay? And you also need the second countable, okay? The only difference is that back then we can find an open set and also homomorphism such that this open set get mapped to some open set in Rn, for example. But this time, because you have things with boundaries, so it's a little bit different. So you might still have open set that's get mapped, or you can say homomorphic to some open set in Rn as the original sense. For example, if you pick a point here, let me use different color. So if you pick a point here in the interior of the manifold, right? So this is the manifold. Then you can definitely find an open set that's called the U alpha, such that you can find a homomorphism, and the set will get mapped to some open set here. And this is open in Rn, right? Or actually open in Hn, but this open set would not intersect the boundary of Hn. But if you unfortunately pick a point on the boundary here, right, on the H, right? So this whole thing is actually, later on you can see that this is the boundary of the manifold. Then if you pick a point, say Q here, then unfortunately, I mean, you cannot have a whole open set around it. So your open set would look like something like this, right? And this whole thing will get mapped to an open set here. Maybe I should use the open. Right, so this is your, that's called phi beta of Q, right? And this is your open set. Right, if I call this U beta, right? And this is what we call the open set in Hn, but possibly intersecting the boundary of Hn, right? So you are essentially going to see two types of open set in this case, right? So either it's the original open set in the usual sense that we know of, right? Or you might have this type of what we call the boundary chart. Namely, your open set, this specific open set will intersect the boundary of your upper half space. So geometrically, you can actually see it. So why I know, and then be careful here, the open set here, actually, I put a dot line here, but if you think about this open set should actually contain the boundary thing here, right? Because think about it, what's the open set in Hn? Under the subspace topology, you take an open set in Rn and intersect Hn, right? So let me put a picture here. If you have upper half plane, right? What would be an open set here intersecting boundary? You're essentially taking the open set or open ball here in Rn, intersecting Hn, right? So when you intersect, you can imagine that it's going to include the boundary line there, right? That's why the open set in Rn, the one that intersecting the boundary, will look a little bit different than the usual open set we know in Rn. So that's the only difference of topological manifold with boundary. So sometimes that we want to distinguish these two, because when we say topological manifold, we automatically kind of assume it's the one that without boundary in the usual sense. So if you want to specify this can be a manifold with boundary, then we will have to say it's a topological manifold with boundary. So you can see that in the literature or in the textbook later on, if they say it's a topological manifold, then usually they mean the one without boundary, okay? And if they want to say something with boundary, they will specify it, okay? So you want to be careful, these two are still a little bit different. And last time we stopped here where we want to make it rigorous about an interior point and boundary point. So we say a point P in the manifold is an interior point, right? If it's in the domain of some interior chart, right? So you can see this is exactly the picture I just drew, right? If your open set get mapped to the usual open set we know of back then in Rn, this is what we call the interior chart, right? If you want to really distinguish those two. And if you have a point Q, we call it a boundary point. If you have a boundary chart such that this homeomorphism map the point to the boundary of Hn. So the point that I just pick up here, this point Q is exactly the boundary point because you can see that through the homeomorphism, it get mapped to the boundary of Hn, right? So that's what we call the boundary point of a topological manifold with boundary. So then, I mean, intuitively, we all know that if you collect all the possible boundary points, then we call it, that's the boundary of M. And we use this specific notation. You already see it in like, in point set topology that when we talk about a boundary in the topological sense. So basically in this picture I just draw, as you can imagine, the boundary will be this kind of roughly a circle here, right? This is the boundary here. Okay. So now there's a natural question we should ask. Natural question, not necessarily an easy question to answer, but a natural and important question is what we call the topological invariance for boundary. Because the thing is that I said, okay, it's a boundary point if you can find a boundary chart such that it get mapped to the boundary of upper half space. But you should definitely ask, would it always be the same if I choose a different coordinate chart, right? Because a lot of concepts, as I mentioned before, in geometry, a lot of time, if you want to define a nice property or a well-defined property, a lot of time you need to make sure that it's independent of the chart you choose. Otherwise, there will be a problem, right? Otherwise, this property is not good enough, right? You can think of that in some sense, coordinate chart is essentially you're assigning a coordinate to this abstract manifold, right? You don't want this property you have here will change once you do a change of coordinate, right? So basically, we can ask the question, okay, is it always the case that if I have a boundary point with respect to one chart, would it still be a boundary point with respect to another chart? It turns out that we can actually prove that. This is the proposition 1.37. Actually to prove it, it's actually much harder than we expected. So I'm not going to do it here. We don't have enough equipment, but at least we can see what's the statement here. So let's say you have a manifold with boundary. then it turns out that each of the point is either an interior point or a boundary point, but not both. Okay, you're not going to see like something that can be both interior or boundary, right? Then there's a big ambiguity here. So this is actually good that we know that interior point and boundary point is separate, like disjoint, right? You don't have this kind of ambiguity that which chart are you using, right? I mean, any chart you're checking, it will always be either interior or boundary, not both of them. So to give you a rough idea about some example about the manifold with boundary is that, for example, you can draw this cylinder surface, right? So I just truncate the cylinder, right? It's a finite length cylinder. So you can think of that you have a cylinder including the top and the bottom, right? Just the surface, right? This is like a two-dimensional surface, right? Then you can think of that this is a manifold with boundary because the boundary is exactly the upper circle and the lower circle. That's called this S1 and S1 here, right? So these two together will give me the boundary of my manifold, right? And also there's another typical example we can see that if you have a closed n-dimensional ball, closed means that think about, okay, a solid ball, right? Like Earth, but including the inside three-dimensional solid ball, including the surface of the Earth, right? So you have a closed ball, right? Everything inside and including the surface part, right? And this is usually what we call the closed ball. And this is also a manifold with boundary. And you can think of what would be the boundary, right? So the boundary of this closed ball is essentially the surface, right? The surface of the Earth. That's essentially the sphere, but with one-dimensional lower, right? So think of that if you have a three-dimensional solid ball, then the boundary of this manifold with boundary is the S2, the usual sphere we know. Think of exactly the situation with the Earth that we live in. Okay, so the whole thing, the solid Earth is the closed three-dimensional ball, while the surface, right, where we live in, the surface is actually the sphere, is the boundary. And you can also have the example that, for example, upper hemisphere, but including the equator, right? So upper hemisphere and including the equator, right? So this is what we call closed hemisphere. This is also a manifold with boundary, right? And as you can imagine, if you call this a manifold, then the boundary will be the equator. Right. So you can actually come up with a lot of example. There's a lot of example with topological manifold with boundary. Okay. But you want to be really careful when we talk about manifold with boundary. The manifold boundary is not necessarily equal to the topological boundary that we know of when we talk about, I mean, before we even talk about manifold, right? So in the sense that you learned in, say, advanced calc, when you learned the point set topology, right? So we want to be careful, right? Like when we talk about manifold with boundary, the boundary is not necessarily the same as topological boundary. So let me give you this example. So just see a concrete example. Let's say you have a unit, because when we talk about topological boundary, that means it depends on what topology you're doing here, right? Because it would be totally different, say, if you regard a manifold or a space as a subspace of some larger space, or if you regard that manifold or space as an abstract topological space itself. So when we talk about topological boundary, we need to be careful what's the topology we use here. Once you mean a total different topology, then the corresponding topological boundary will be different. So you want to distinguish this too. So for example, let's say I put a two-dimensional disk in R3, right? This is essentially a closed unit ball, like B2, or you can say the disk. Okay, so essentially, let me put it this way. Let me just put some round disk horizontally, right? So this is a two-dimensional disk. Doesn't matter how large it is. I mean, you can say that it's a unit radius or doesn't matter. right? Including the boundary, it's a closed one. Okay, so as a manifold, right? If you think of B2 as a manifold, then it's a, so B2, or you can think of this as M, right? Is a topological manifold. Actually, I want to be specified, topological two-dimensional manifold with boundary, right? And the boundary is actually, in this case, the manifold boundary is, we know, right? Just the circle here, right? This is the S1, the circle. Okay. So as a topological manifold with boundary, we know that the boundary is a circle. Okay. So basically, this is a manifold boundary. But what about as a topological boundary, right? If you view this B2 as a subspace in R3, right? So the topological boundary as a subspace in R3 is actually the ball itself, the closed ball itself. Okay, so think about this, right? What's the original definition of topological boundary? It means that it's not in the exterior nor the interior, right? And here, because you are using the topology coming from R3, right? So your open set in R3, it's actually an open ball, right? So you want to be careful that you can see if you are using a topological, if you're using a topology coming from R3, then your topological boundary becomes the manifold itself, right? While when we talk about itself as an abstract topological manifold with boundary, the manifold boundary is the circle. So you want to be a little bit careful here. This is one of the examples that I put it out from the textbook, so you can also read it. It's kind of hidden in the paragraph here. So you can think about the subtlety here. So I just want to give you a heads up that you want to be a little bit careful when people say boundary. You need to ask, are you talking about the boundary of the manifold or actually as a topological boundary of some topological space? So those two are not necessarily the same. It might coincide, but it may not be the same. Okay, so to have a little bit more terminology here, later on when you read a little bit more literature or maybe read a paper in geometry field, you will see a lot of people call a manifold to be a closed manifold. Usually when we talk about closed, it means the manifold is compact and without boundary. You might have a manifold which is compact but has a boundary. For example, the two-dimensional ball, right? Or a two-dimensional disk, or a lot of things are compact, but with boundary. So when we say closed manifold, we say it's compact and without boundary. So what's a closed thing? Sphere is a closed manifold without boundary. Okay. So there's some other example here. So this is just a terminology that we might encounter in the future. Or if you read some like academic paper, then you will see this type of terminology. So from now on, I'm not going to prove anything because in the sense that like topological manifold with boundary has a lot of common feature with topological manifold. So a lot of property are exactly the same as what we know before. Okay, so first of all, the proposition 1.38, this is kind of we already know from like what we learned before in the sense of topology. So first of all, if you collect all the possible interior points, right, and we call the interior of the manifold, you can imagine interior should be an open subset of the manifold. And since it's an open subset of manifold, I think we discussed this before. If you have an open subset of a smooth manifold or a topological manifold, then this open set should be a topological manifold and with the same dimension. And this open set is not going to have any boundary, right? So think about like this is the interior of manifold. And whereas if you are considering the boundary of your manifold, then the boundary should be closed. right? You can use the example I just mentioned to cook up an example here. And the boundary, it's going to be one-dimensional lower, right? So it's going to be n-1 dimensional manifold. So you can think of if you have a three-dimensional solid ball, then the boundary is the sphere, which is two-dimension, right? And as a topological manifold itself, if you view it as a topological manifold itself, the boundary is a manifold without boundary. So when you ask what's the manifold boundary of the boundary, then it's actually there's no boundary here. So you should be a little bit careful. This here everything is in the sense of manifold with manifold boundary, and we only say that a manifold with boundary is a topological manifold if and only if when the boundary is actually empty. This is the distinguishment I was emphasizing, that we usually don't regard topological manifold with boundary the same as manifold. It can possibly include topological manifold, right? But we only call it a topological manifold when the boundary is actually empty. Okay, so which means that we actually want to distinguish these two, okay, because they're quite different. One is locally Euclidean, the other is locally HN in some sense. And I don't want to spend like waste my time on like stating the proposition 1.40, but essentially what I can tell you is that 1.40 just listed all the topological property that we saw before. For example, back then we learned topological manifold is locally path connected, and also locally compact, and also pericompact. All these topological property are shared here. So we already know that, so we can actually easily prove. It's just a little bit modification of the proof. So topological manifold with boundary also carry the same topological property. You have questions?
Yeah. I was wondering, for proposition 138, is there a reason why you didn't we didn't talk about D, that if n is equal to 0, then the boundary is not as empty and M is a zero manifold?
Oh, no, there's no, I mean, I just thought that like people can read it, so I didn't want to like specify it. Yeah, I didn't, I just skip it. Yeah, there's no,
if there was a specific reason why not.
Oh, no, I just thought that it's actually easy enough that people can actually like read it themselves. That's why I didn't mention specific. Sometimes that I just don't have time to mention every single, but it doesn't mean it's not important or it's not correct. If it's not correct, I will tell people, right? But I just assume that when people go back to read the 1.38, they will see everything. Yeah.
Got it. Thank you.
Okay. Yeah. So for 1.40, I would just probably put this way. I'm a little bit sloppy here. I just say most of the topological property of topological manifold apply to manifold with boundary. Okay. Anyone have more questions?
Sorry.
Oh yeah, no problem. Yeah, because I hear the sound, so that's why I thought someone want to ask questions. Okay, so now once we can define topological manifold with boundary, then we should be able to define like smooth structure in a similar sense, right? And as I said, I mean, okay, even though topological manifold with boundary is still a little bit different than the usual topological manifold, but you should think of that the way we define things or smooth structures should be almost the same. The only difference is that, okay, later on you might map an open set on the manifold to some open set possibly in Hn, which means it possibly intersect the boundary of Hn, but it should not change anything, right? It's just you need to do a little bit like treatment carefully. So when we talk about the smooth structure, it matters what does that mean to be a smooth map from some open set in Hn to any Euclidean space. right? Because now you might include some boundary points. So for example, we said that I want to recall that what we know of from advanced calc. So let's say if you have an open subset in Hn, this open subset can be any type, right? It could be the original open set that does not intersect the boundary, or it could intersect the boundary as well, right? Then how do we define a map from such open set in Hn to any Rk, right? So we say it's smooth if for each point you can find a larger open set U delta containing this point. And this U delta is the open set in the usual sense in Rn. And you can find a smooth map defined on this slightly larger open set, such that when you restrict it back to the intersection of those two sets, it's going to coincide with your original map. So what does this mean? So think about what do you mean by, so imagine if like in calculus, we have, let's say you have a, if you know that, okay, let me say, if you have a smooth map from an open interval to Rk, then we know what does that mean, because you don't need to worry about taking the derivative on the boundary point, right? Because you can say, oh, okay, at any point inside this 0, 1 interval, as long as I can prove that it's the derivative exists for every point inside this interval, then I'm done, right? Or you can say, okay, C infinity, then you want the derivative to exist, right, for any order, and it's also continuous. But the issue is, what if you're talking about a set with like a closed set, right? Then everything within 0, 1 open interval is fine. But what we worry is how we make sense or define the derivative on 0 and 1. You only have one side derivative, right? So how do you talk about a map from a closed interval like this to Rk is smooth, right? How do you justify it? So what we're going to do is, okay, let's say this is called small f, right? How do we know that it's smooth, or how do we define it's smooth on such closed interval? What we're going to do is, okay, let's take, if you can find an interval a little bit larger, right? For any point, if you can find an interval a little bit larger. So if you can say, okay, I'm going to find maybe some interval like this, slightly larger, doesn't matter. For example, maybe minus epsilon n, right? Something like this. If you can find another map, let's call it F, such that this capital F is smooth, right? And at the same time, when you check the larger interval intersecting the original domain you want, when you restrict it on this domain where they overlap, this capital F you find coincide with the original map. If this is the case, then we say the small f is smooth. That's how we defined or how we justify what is a smooth map for an open set, or for an open set on Rn. On Hn, because open set on Hn possibly might include the boundary point. So this is the treatment. Okay, so let me show you another picture here for Hn instead of the closed interval. So what we are going to do is, okay, let me push that a little bit. Okay, so let's say you have Hn, right? So Hn is everything on top here. Okay, and so you have a open set here, U. But the open set in Hn in this case might contain the boundary. So technically you have like an open set like this, including the boundary, right? So then you say, okay, how do I justify smoothness at this boundary point, right? So then what you're going to, so this is, say you have a map F, right? Actually, in this case, I want to do capital F to some Rk. I don't care here, right? So to say that this F is smooth, what I'm going to do is, if at this boundary point X, I can find an open set in the usual sense. This is what I call U delta, such that this F delta is smooth. And when you take a look when these two set intersect, right? If at this shaded region I draw, F tilde coincide with the original map, then I say F is smooth. So from now on, if we have this open set in Hn, or possibly like open set with including the boundary point, then when we talk about a map to be smooth, we are talking about in this sense. So as long as you can enlarge your domain a little bit and you can find another smooth map such that it coincides with the original one in where they overlap, then we can show that this is a smooth map. So please keep in mind that this is what we are going to what we mean by a smooth map for any open set in Hn from now on. So this is the treatment that we need to do for manifold with boundary. That's the only subtlety or the change here. Everything else is the same. Everything else regarding how we define smooth atlas or transition map being smooth or smooth structure, all the same thing. The only difference is that you need to be a little bit careful when we talk about smooth map from an open set in Hn. That's it. Okay, so this is the treatment here. So, okay, so then before we move forward, I want to give you an example here as what I just said about the smooth map, right? So for example, let's see. So if you said, take the open set to be an open disk intersecting H2. So this would be something like this. Maybe, let me draw a better picture. So let's say something like this, including the boundary, right? So this is U, okay? And then you have a function from U to R defined as the following. So F is 1 minus X squared minus Y squared, okay? But keep in mind that all the XY are actually within this unit ball. So in this case, like your radius, your point has radius less than 1, okay? So I claim that this is actually a smooth map despite the fact that the domain contains the boundary point. So the reason is I can easily extend this map to a larger open set and it will still be smooth. So essentially, the upshot is F is going to extend smoothly to the whole ball. So if you think about it, if you look at the larger ball, unit ball like this, right? The same map F would still be smooth, right? Actually, this whole thing on the ball is actually smooth, okay? So, and if we restrict back to where they intersect, that's the original domain, they will coincide because you're using the same map, right? So F extends smoothly to be the open ball by the same formula. So this tells us that F is smooth on this open set in Hn. But I can also give you a counter example where this might fail. So let me push a little bit down here. So this is the second example. These are all examples from the textbook. I just kind of put it out. So because we are actually at this. So if you have this function G, right? This is continuous on the same open set that I mentioned about, right? It's even smooth in the interior of the upper half space, right? So it's smooth, everything is fine, like in the interior, right? But the problem is that at the boundary, there will be an issue, okay? So the boundary has a problem, but it has no smooth extension to any neighborhood at origin. Actually, to be more precise, what happened, the bad things at origin in Rn, right? So why this is the case, right? Think about what happened near y equals 0, right? So if you check the derivative with respect to y, right, this is going to goes to infinity if y goes to 0, right? So even you extend the open set, right? Let's say even you can, the problematic point will be at the origin. Even you extend the original domain a little bit larger, right? You say, okay, because you want the derivative to be continuous, right? Because you're looking for a smooth C infinity function. But then if you check the derivative, you will see if I require the extension to coincide with the original function in the original domain nearby 0, then the derivative should match, right? And on the boundary. But you can see that the original derivative, which is the partial derivative to y, will actually goes to infinity, no matter how you extend your function anyway, right? So basically this tells you that in this case, this function g is not going to be smooth in the whole u, because actually I should say it's not smooth at the origin. That's the problem. So you can see that you will have some situation where a map can be is smooth in an open set in Hn, because it can extend a little bit more beyond the boundary point. But you also can have a problematic map which is not smooth at a specific bad point here. So you want to see that this is the treatment of how to justify or check whether a map is smooth when you have this kind of spatial open set, including the boundary here. Okay, so now we can, once we make sense of such a smooth map, then essentially the collection of all the charts whose domains cover the whole M, plus if all the transition maps on diffeomorphism in the above sense, then we called it a smooth atlas. So the definition of smooth atlas or the smooth structure are exactly the same as before. The only difference is a little bit difference is how we define the smooth map, right? Like if it's an open set in Hn, then you need to be a bit careful. But everything else is the same. So what's a smooth atlas? You collect all the charts, like where the domain can cover the whole M. And also if you collect all the all the transition maps on diffeomorphism, then this gives you a smooth atlas. And what's a smooth structure? Same thing. You collect the maximum smooth atlas, then that's my smooth structure, right? So basically, with this is what we call the smooth manifold with boundary. So once you can define a smooth atlas, then it will induce a smooth structure with a smooth structure on a topological manifold with boundary, and that gives a smooth manifold with boundary. So everything is the same. The only difference, as I said, is that when we talk about smooth map, we mean by the above sense, right? Because you might actually have a smooth map from some open set lies in Hn. That's the only thing you want to be a little bit careful. And everything else, like there's some other things I skip in the textbook because they actually mention a lot of terminology, which is exactly pretty much the same thing. So I'm not going to like write it down, but I just give you a couple of them, for example. So you can also define the so-called smooth coordinate ball in this sense, right? Coordinate ball. Actually, in particular, you can also define the smooth coordinate half ball, right? So imagine back then, what's a smooth coordinate ball in the original sense? It means you have an open set in the chart that's homeomorphic to an open ball in Rn. But now, because with topological manifold with boundary, you might actually have a set that gets mapped to an open half ball in Hn, right? So for example, you might have an open set on the manifold, right? Right, this manifold get mapped to a half open ball here, right? So if this is the case, then we call this the smooth coordinate half ball. Okay, so we can define the same terminology as before, but right now we have a little bit different open set here. So we might have some extra term here. And with this, we can also define what we call the regular coordinate bowl or actually half bowl as well. So I'm not going to write down the detailed definition, just to tell you that you're going to see it in the textbook. A remark I want to make here is that back then we know if you have a bunch of smooth topological manifold, no boundary, okay, without boundary. If you do product of them, I remember one of the example is you can if you take at least finite product of smooth manifold, it would be a smooth manifold, right? But here you may wonder, okay, if I have a bunch of manifold with boundary and I do product manifold, would it still be manifold with boundary? It turns out that it's not necessarily the case anymore. Okay, so this is the remark you want to be a little bit careful, is that a finite product of smooth manifold with boundary may not be a smooth manifold with boundary anymore. Okay, in our sense. Okay, so let me give you an example why this is the case. So think about you have H1, which essentially is the upper half, it's a half interval, right? R1 is the whole interval. H1 should be a closed half interval, right? Think about what's H1 closed H1, right? So think about if you take product of this half closed interval and product itself, right? You can imagine it should give you the first quotient. Right, this is the product, right? So this is the first quotient. This is 0 to infinity interval, product 0 to infinity, right? And you can see this is not even locally homomorphic to Hn, right? So this is a spatial manifold. We give a spatial name. This is what we call manifold with corner in some sense. So this is manifold with corner. So this is probably the major difference here. If you have smooth manifold without boundary, you do product, it will still be smooth manifold. But if you have smooth manifold with boundary and you take the product, it may not be smooth manifold with boundary anymore. It may be something what we call the smooth manifold with corner. Okay, so you want to be a little bit careful here. This is the subtlety and the difference. Okay. So the next two proposition, I'm not going to prove it, but the 1.45 is essentially justify or essentially kind of comments on what I just said, that you need to be careful when you take product of smooth manifold with boundary. But it turns out that if you only take product of one smooth manifold with boundary with other thing which are nice, then you're fine. So let's say if you have K of smooth manifold, whatever K is, and one of the manifold that's called the N is a smooth manifold with boundary, okay? Then you do product of them, meaning among this product, only one manifold has boundary, then you're good. Then this product, the product would be a smooth manifold with boundary. And you can actually identify what's its boundary. Intuitively, we know the boundary of this product manifold, it's going to be another product manifold where the last one is the boundary. If you think about it, just take R1 cross the interval, right? And this is going to give you the closed upper half plane, right? You take the whole R1, right, cross the half one, then this would be the upper half plane. And Hn is indeed a manifold with boundary, right? So if you only one of them has boundary, then you're good. More than one, then you may have problem. That's what this proposition is talking about. Yeah, so you can, this is actually not hard to prove. You just really literally using the definition and write it down. Okay, so the last thing I want to show is that this is the what we call the smooth invariance of boundary. So back then we say that there's a topological invariance of boundary. This is the smooth one. So involving the smooth chart. And it's pretty much the same, saying that no matter which smooth chart you use, a boundary point should always stay boundary point. Doesn't matter which smooth chart, okay? So let's say you have a manifold, smooth manifold with boundary, and you have a point. If you can find one smooth chart such that it maps the point P to the boundary, that means P is a boundary on the boundary of manifold, then the same thing is going to hold for every other smooth chart when the domain contains this point. This is basically same thing. It's just now we make it a little bit, in some sense, we make it a bit stronger in the sense that like it involves the smooth chart, not just the topological chart. Okay, so this is basically tells you that no matter which smooth chart you use, if one of the charts maps a point to boundary, then other chart will do it as well. Otherwise, there will be a problem. Okay, so any question so far? So I think it is not too bad, I hope. Okay, so I actually include the smooth manifold chart lemma I mentioned at the beginning, but as I said, I don't think I have time to prove it. So what I'm going to do is just to write the sketch of the things I suppose I want to do back then, and I will include it in this lecture notes so you can take a look later on. It's just a minor correction or modification of what textbook was doing. So if you want, you can also read the textbook so you can see the proof. So I'm going to definitely move on to the smooth map. And so this smooth map in chapter 2 is actually, if you took the curve and surface before, you're going to see that this is pretty much exactly the same thing as how we define a smooth map between two regular surface or between a surface and RK. Exactly the same treatment. So back then, what we did is we essentially, what does that mean to have a smooth map from regular surface to R, for example? Then you essentially use the coordinate chart you have there on this regular surface, then you compose with the phi inverse. Then if you can say that that map is smooth, then the original map is smooth. It's exactly the same treatment. The only difference is now we replace regular surface by any smooth manifold we want. Okay, and when we talk about smooth map, most of time, I mean, in order to define this concept, like to make it well defined, we need to use smooth manifold. Okay, it kind of almost doesn't make sense to just talk about topological manifold at this point. Okay, so sometimes that when I talk about smooth function or smooth map, I may not necessarily write down it's a smooth manifold, but the default is you should just assume it's a smooth manifold. And in this textbook, you are going to see they kind of use two different terminology. So first is when they talk about smooth function, what they mean is that it's a function from smooth manifold to Euclidean space Rk, when k can be bigger than or equal to 1. Technically, I can also talk about when k is bigger than or equal to 0, but 0 is a little bit spatial case, it's a little bit boring. And when they talk about smooth map, what they really mean here is it's a map between two smooth manifold. So they kind of want to make a distinguishment here. Okay, so when you read the textbook later on, you will see that they kind of, sometimes they say it's a smooth function, sometimes they say it's a smooth map. That's the difference here. Okay, and of course you can think of smooth function is a spatial case of smooth map, right? Because this n can be any smooth manifold. So if n is Rk, then it's a smooth function, right? So you can think of smooth function as a spatial case. So then now how we define smooth function, right? So we start from smooth function, but you can imagine smooth map will be similar. So let's say you have a smooth M manifold, and if you have a function from M to Rk, we say it's a smooth function if for every point in this manifold, you can find a smooth chart such that P is in the domain of this chart. And when you compose with the inverse of this chart, this would be a map, a smooth map. This open set is going to be in Rn, right? Because we are in the n-dimensional manifold. Then we say as a map from Rn to Rk, it's smooth on the domain. So first of all, I'm not going to review what does that mean for having a map to be smooth from Rn to Rk, right? This is the scope of advanced calculus, right? So let's say you have some, let me just quickly say, let's say you have a map from Rn to Rk, right? So you will input some n coordinate. Output, you might have like k component, right? So to be smooth means that each component function need to have, you can take derivative infinitely many times, and each derivative should be continuous as well. This is what we meant by smooth. So we are building on the understanding of what does that mean to have a smooth function from some Euclidean space to another Euclidean space. Okay, that's why we really need a lot of knowledge actually from advanced calculus. And actually this textbook also did a pretty good job by including a lot of like a review thing in the appendix. So every now and then you will see that they will refer to, I don't know, appendix, I think it's in C or something like that. Okay, so let me draw an indication picture. This is the picture I always find it very helpful when I need to consider this smooth map like this. So let's say you have a, let me use different colors here. So you have a smooth manifold. I want different color. Smooth manifold M, right? And you have a map to Rk, right? Some n-dimensional case, right? And you say, okay, I want it to be smooth on M. What does that mean? So it means that, okay, for each point P, right? And you might, if you can find a chart, U alpha, and this chart, of course, is get mapped to Rn, right? To some open set. So this is your V alpha of U alpha, right? And then instead of, so we cannot directly talk about what does that mean to have a smooth function from an abstract manifold, right? What we can do is we consider the diagram like this, right? We know what does that mean to have a smooth map from Rn to Rk. So we consider the map like this, because you can actually go backward by phi inverse, right? So if this map is smooth from its domain, then we say f is a smooth function from M to Rk. And if you really, really recall, this is exactly the same treatment as what you saw before in curve and surface. That's why I keep the definition back then, because it's actually a definition that can be easily generalized to the situation here. That's why I need to require people took 720 before, right, to take this course. Okay, so any questions so far? This should be very familiar at this point. So now we can also talk about a spatial case, right? So when I say M to Rk, right? A spatial case when K is 1, meaning your target is R, right? Then you could, this is a spatial function, what we call smooth real valued function, because I mean the target, the output is real value. So if you collect all the smooth real value function on M, then in literature we usually use the C infinity of M. This means that it's the set of all the smooth real valued function. Okay, and this smooth real value function is actually itself a vector space, a real vector space. Okay, so it actually has a nice, in some sense, has nice algebraic structure. We are going to see this a lot later on when we learned how to do tangent space and so on, or calculate, I don't know, tangent vector field and all that. We are going to come back to this spatial vector space. Okay, but just to tell you the notation here. And this is actually this lemma or exercise is in the textbook, but written as an exercise, like like all this small exercise in between paragraphs. So I called it a lemma or exercise. Okay, but it's I want to prove it because it's actually quite important. So just now, what's the definition of being smooth? It means that if you can find just one smooth chart around the point, such that the composition F composed phi inverse is smooth, right? But the question is, if for the same point, if I pick another chart, right, for the same point P, I may have other charts. So for example, U beta, this domain might still include P, right? So if I use other charts, would they still be smooth, right? I think we also discussed this before when we learned the smooth map from regular surface, right? You don't want to have the ambiguity where with respect to one chart, your function is smooth and suddenly it changed with different chart. So the good thing about smooth structure is that, remember, the transition map between charts is actually already smooth. So because of that, it will make our definition here well-defined. So we're going to see this. So this is essentially the lemma says here. If you have a smooth, smooth manifold, either with or without boundary, and you have a function from M to Rk, we say this is smooth in our sense above, if and only if it's going to be smooth, this function F composed phi inverse is going to be smooth for every possible smooth chart in your manifold. Okay, and to prove this is actually not hard at all. It's exactly to take the advantage that transition map is diffeomorphism. Okay, so this is smooth, and this is in fact only if, right? So one direction is easy, right? Backward direction is obvious, right? If this function F composed phi inverse is smooth for every chart, it's going to be smooth for one chart, right? So it's quite obvious. So one direction is trivial. The other direction is actually not bad at all. As I said, you just use the transition map, right? So you said that, okay, I'm going to have pick one point in M, right? So I say, okay, if it's smooth, that means you can find a chart, one of the chart, right? Such that X is in this chart. Oh, sorry. And by the definition that this chart, the F composed phi inverse, phi alpha inverse, should be smooth. Now, the only thing I want to check is that what if this X lies in another chart where the map F composed the other chart of the inverse will also be smooth, right? So now if X is in another chart, right, then let's check what this map looks like, right? So this map should be from the domain. The domain will be a bit different, right? Because now you can only consider where they intersect each other, right? And first of all, even in this domain, X will be in it, right? And this whole thing is actually lies in the domain phi b of U beta, right? Phi beta of U beta. Okay, so what this map is. So I can rewrite this in terms of the composition of two smooth maps. Right, so F composed phi beta inverse is the same as F composed the chart that's already smooth, and compose my transition map. Right, and it's also smooth, right? So then, of course, you have, and those two maps are actually smooth, both smooth function from some Rn to Rk, for example, right? So then we know that this new function F composed phi beta inverse is going to be smooth. So this thing is smooth in some neighborhood of this point, right? So, and X is arbitrary. So that means it turns out that this map is smooth on the whole domain. Right, so back then we have a slightly small neighborhood, but since X is arbitrary, so you can actually find you can have a derivative for every point in it. So this tells me that this new function f composed v beta inverse is going to be smooth again. And this is arbitrary chart that you choose as long as they overlap. So this proof tells us it really doesn't matter which chart you're choosing, right? As long as you have a nice smooth structure, which means all the charts are smooth compatible with each other. And that's exactly why you can see now why we need smooth compatibility. Without smooth compatibility as part of the criterion for smooth manifold, then you will have a problem defining smooth map, because you will possibly have a map which is smooth with respect to one chart and suddenly not smooth anymore. You don't want that to happen. So this essentially tells you, if you know you have a smooth structure, and if you can only find one chart that make it smooth, right? If you can find one phi alpha such that F composed phi alpha inverse is smooth, then it's going to be smooth for every chart. So you only need to check one chart. That's the whole point. And that's the beauty of it. Okay, so now this spatial function that we just saw here is what we call the coordinate representation. So if you have a function from M to Rk, and you have a chart, right? Whatever that chart is. And remember the function that we care, it's essentially F composed phi inverse, right? Phi is one of the coordinate map. Then this is what we call F head. And this F head function is a function from Rn, if n is the dimension of manifold, to Rk. This function is what we call the coordinate representation. So a lot of time, people actually, in some sense, identify, we identify F and F head, right? When we talk about, a function from a manifold to Rk, a lot of time when people really write it down in terms of the coordinate, they were actually using F head. But in some sense, we just regard it as the same, because this is essentially one way to write down F in terms of its coordinate. So a lot of time you will see that sometimes, I mean, if in the future, if you read some paper, a lot of time they might just kind of identify those two or abuse the notation sometimes. Okay, so this is what we call the coordinate representation. And we just proved that if F, or actually by definition, the map F is smooth if your coordinate representation is smooth for one coordinate chart around each point, right? This is the definition of being smooth, right? So in other words, what do you mean by having a smooth function from manifold to Rk? It means that your coordinate representation is smooth, because coordinate representation is from Rn to Rk. If this is smooth, then that means F is smooth. So let me show you a quick example that this is essentially the example from the textbook as well, but I think it worth like mentioning here. So let's say you have a map from R2 to R. If you think of R2 as a manifold, right, smooth manifold, and that's in this case, I don't want to use the standard structure of R2. I want to use the coordinate, the polar coordinate. And in a specific smaller domain. Okay, sorry, I want X to be positive, doesn't matter, one of the domain, right? So let's see, so let's say I have R2, I'm just drawing the picture here, so it helps me to think. So this is R, right? Okay, and you have XY here. But instead of using xy, I want to use a specific coordinate, which is polar coordinate, right? R and theta, right? And this is from R theta to that, this is phi inverse, right? And what's the phi inverse? Essentially, you want to plug in. So going this direction is phi, right? From the manifold to R theta. But going backward, right? How do you represent x and y in terms of polar coordinate? This is R cosine on side, right? So you can think of polar coordinate as just a different way of representing the usual coordinate, or you can think of in some sense change of coordinate, right? So if this is the case, what will be the, if you use this particular chart, phi inverse, right? Then what will be the map, the coordinate representation? Right, so you have x squared plus y squared, that's just r squared. And you can see that this is smooth as a map from r theta to r squared, right? So this is one way to view it, right? So you can see that you might have so many different ways to give some manifold a coordinate, and depends on the coordinate you choose. If you choose a nice coordinate, you can rewrite an ugly map into a much simpler representation. And the simpler representation can sometimes give you a easier, it can make you check whether it's smooth much easier. So a lot of time, sometimes you need to work with a nicer coordinate, right? Then it will save you some time. So we're going to see more complicated example in the future. So now if you can accept how do we define smooth function, then now change the target to be another manifold, then it's the same idea, right? So now we have both M and N are smooth manifold. Then we can define, like, what does that mean to have a smooth map from one manifold to another manifold? The same idea, right? Back then, because the target is RK, so we just leave RK as it is. But if it's between two manifolds, then you can imagine you need to compose both sides. You need to compose the coordinate chart, right? So you want to compose the coordinate chart in a way that eventually it becomes a function between one Euclidean space to another, right? So we say it's smooth map if for every point in a domain, you can find a smooth chart U such that P is in this U domain U. And you also can find a chart on the target on N such that the image f of P is in V, right? But we need one extra condition such that you want the chart, when you choose the chart U, you want that the image of this chart is actually contained in V. Okay, this is actually important. If you don't have this, then you might have a bad example later on. This is in one of the homework problems that you can check that I think I want to assign this, that there's a weird example where if you take out this red things, this condition I circled here, there may be problematic map here. There will be a problem with this definition. So once you have this f of u lies in V, then we say capital F is smooth if and only if this map is smooth, right? So let me just draw the picture. It's easier to see the picture. So you have a map, you have a manifold M, right? Map to some other N, right? I say, okay, how do I know this is smooth, right? So I say, okay, for every point P here, I can find a smooth chart U containing this point, right? And up here, I have f of P, right? I also want to find a chart V that's including the f of P. But I need an extra condition where f of U is contained in V. So this is f of U, right? And if you call this U, okay? And when we say f is smooth, it means that now we need to pull back to Rn, right? So let's say if M is m-dimensional manifold, and capital N is n dimension, okay? So then you will pull back to M, right? So from phi, you will map to phi of U. Okay. And the other way, you also have a chart here, right? From V. So this might goes to some other dimension that's called it Rn, right? And you have an open set here. So this is per psi of V, okay? And instead of looking at F, what you do is you look at this, right? And this is exactly per psi compose F compose V inverse, right? And this is exactly the coordinate representation, the F hat that we meant. And you can see that this becomes a map from an open set in Rn to an open set in Rn, right? From Euclidean space to Euclidean space. So we know what does that mean to have a smooth map here. So this is exactly the definition. If you're talking about a map from between two manifolds, what does that mean to be smooth? It means that your coordinate representation F hat is smooth between two Euclidean space that we know of. And this is the diagram that we usually use to give you an idea that, because sometimes you need to do like you need to see the diagram to see that which one compose which, right? So this is what we call the coordinate representation. Same thing of F, same idea. And exactly like what we just saw, you can actually check, I'm not going to check it for you, that F is smooth, right? If and only if your coordinate representation is smooth for every pair of smooth chart, right? So when it comes, just now when we talk about smooth function, we prove if it's smooth with respect to one chart, it should be smooth for every single chart, right? Here, same thing. If capital F is smooth, then it means, by definition, originally, it means the coordinate representation is smooth for one particular choice of the charts from both M and N. But you can actually use the fact that each transition map on M or on N are all smooth or actually diffeomorphism, right? Then you can actually easily prove that it doesn't matter which choices of phi or per psi you choose, the same thing will still hold, right? It will still be smooth. That's why it says the coordinate representation will still be smooth for every pair of smooth chart of M and N, okay? And the last thing I want to quickly show, since this is very easy, and then we are talking about the smooth already. So a quick, easy proposition that in the textbook says, I mean, we already know that every smooth map is continuous if we are talking about smooth map between Euclidean space, Rn to Rn, for example. But would this still be true for map between manifold, right? We want it to be true, right? Otherwise, it will be odd. But it turns out that it's definitely going to be true. So let's say you have a smooth map from between two manifolds. Then this is just means that your coordinate representation, is going to be smooth, right? This is that by definition. Right? So this is the definition of having a smooth map between two manifolds. But now, because this coordinate representation is a map between two Euclidean space that we know. And in Euclidean space, we know that if a map is smooth, of course, it's going to be continuous, right? This is something we can say, right? Then, okay, then we can stop here for now. Now, we also have this phi, right? This is the coordinate map, smooth chart, right? One of the smooth coordinate map. And also the per psi as a smooth chart. So this is from M, right? From N. This is also, they're all homeomorphism, right? This is the what we have back then. Okay. And if they're homomorphism, inverse and itself is continuous, right? So if you look at this original map restricted on U, you can rewrite it as a composition of three continuous functions. This is the same trick over and over. right? So you can see that this psi inverse is continuous because psi is a homomorphism. This is also continuous, right? We just said as a function between Rm to Rn. This is continuous because it's a chart. So definitely composition of 3 continuous map is continuous. And because you can choose any charts, right? So essentially, because capital F is continuous and in each open neighborhood, right? So it's going to tell you that F is going to be continuous on the whole M. So this is just to take the advantage of the homomorphism, the coordinate chart we already have, nothing fancy, right? And play around with the definition. So you can see that indeed the way we define smooth map between 2 manifolds are nice in the sense that it's independent of the chart you choose. It's also continuous. Okay, so there's no bad definition here. Okay, so I'm going to stop here. So coming back on next Tuesday, I'm going to give you all the property between for smooth map. But from now on, you can see that this is actually very the same as what we saw before, the treatment that we saw in curve and surface 720, right? So if you still have, if you want to kind of compare, it's highly recommend that you go back to check the definition back then, right? Regular surface is just a spatial case for 2-dimensional manifold, right? Like every treatment is the same, okay? So yeah, so I'm going to stop here. If you have any questions, let me know. But thank you for coming, all 3 of you. Like I know this Saturday, so yeah. So I will see you on Tuesday, and I'm going to post the homework by the end of today, the new one. So since it will be like closer, so I'm going to like probably this time the homework 2 part 1 will be a little bit shorter, definitely, because we cover a little bit lesser than what we can do, and then the time is actually shorter. So yeah, so just after today you can start working on homework 2, and I hope from now on the chapter 2 supposed to be easier in the sense that it's more analytic, like it's more concrete, you can calculate things, and also you should feel much more familiar, right? It should be something that you already saw before, worked with before. Okay. So let me know if you have any questions. Thank you for coming.
Thank you. Have a nice
Thank you.
day.
Yeah, you too.
Bye.
Bye. Thank you.